I think on Friday we were looking at this idea of an increasing and decreasing interval of a function. So here we have an example of a function, fourth degree function. And if you take a look, we start out somewhere out in infinity and move from left to right. Until we get to -1, we find it's increasing. So it's increasing on that interval. And then we can see it's decreasing at that point, down to 0, on that interval -1 to 0. And then again, it starts increasing again up until we get to 2. And then finally, the remaining interval out to infinity is all decreasing. I bring this up because, well, a lot of the functions, certainly all the polynomial functions we're going to look at, have this feature that they're kind of smooth. We're not looking at a piecewise function. You could just draw the whole function with a pencil without taking the pencil off the paper, if you're very careful. And there are no sharp kind of, edges like the way an absolute value function might change direction. When you have that, and you have a change from an increasing to a decreasing interval, you get something here which we call a local maximum. That is a point where, if you go on either side of -1, the value is going to decrease. Similarly, here at 0, we have a point which is a local minimum. It's where we go from decreasing to increasing. And again, if you step a little to the left or right at this point, you see the function will move up. So that's an important feature of a function. Maximums, local maximums and local minimums. The book gives us a really, again, a kind of an obscure seeming definition, but let's go over it. So a maximum is the function at some point A such that A is a member of some interval, and for all the x's that are on that interval, f of A is greater than or equal to f of x. So let's just kind of draw a little piece of this, and let's look at the minimum later. Let's look at this maximum here. So what it's saying is if we pick some interval that our maximum, our A is at, this is our A, this is our f of A. If we pick some interval here that the A is on, if we choose any x on this interval, then the function is either going to be equal to f of A or it's going to be less than. That's what that definition means. There's, of course, the equivalent minimum definition, which looks pretty much the same. We have an A and a function at A. A is on some interval, and for all x on that interval, f of A is going to be less than or equal to f of x. That would be local minimum. We don't have tools to find these maximums and minimums in most circumstances. In some circumstances we will. For example, if I had some function y equals, say, x minus 2 squared plus 3. Well, this is going to be a parabola. And the minimum on this parabola is going to be at its vertex, which we can figure out. Later on, if you go on to calculus, you have some very nice tools to figure out where local max and minimum are, but we're not going to be involved with that. You could use your graphing calculator, and if you plug in a function, you'll notice that there's a feature under calc that says find the minimum or maximum. You have to be careful. You have to start, looking in the right place. You have to look at the result it gives you and see if it makes sense. And it's an approximation too. We may be able to figure out an exact value, whereas the calculator may only be able to approximate it. So maximum, need to know what a maximum and a minimum is, but again, except in very specific circumstances, I guess we had an absolute value function, right? You can see that you're going to have a minimum in this case, not just a local minimum, it's a minimum of the function. All right, any questions about that section? Before I go on, we're getting close to the exam, and I don't want to leave people behind on stuff. Is there any, I'm going to have office hours today if you want to come in and talk about homework problems, but were there any problems on the homework that were particularly egregious, particularly difficult, or seeming impossible? While you're doing that, who came in? Saw somebody come in. Yeah, Aaron.
JC.
I have homework for you. You wear hats, I'll never recognize you. Yes.
I also came.
You're Stephen?
Yes.
Okay. You're Stephen Ramsey.
Yeah.
Are you Ramsita? Okay. You don't hear any questions on homework, so. All right. The next section we're going to cover is on something called a transformation. That in here. Transformations on functions. And And before we get to the nitty-gritty, I want to remind you of something that should be familiar. If I write down the equation of some circle, say x minus 2 squared plus y minus 3 squared equals, let's say, 4 or 2 squared, you should know that the center of this function, center of this circle is not a function. Well, we look here and we see x minus 2, so that's 2, and y minus 3, and that's 3. So we go to 2, 1, 2, 3, that's the center of my circle, and it's going to have radius 2. Similarly, if I had, say, x minus 0 squared plus y minus 0 squared equals 1 squared, well, now that's just a circle at the origin with radius 1. And let's do one more. Let's say I had x plus 4 squared plus y squared equals, I don't know, 9, 3 squared. Well, now wait a minute here. And this was 0, 0, clearly. This, it's not at 4, right? It's what you're subtracting. So we would subtract the negative 4. So we expect this to be at negative 4, 0. So 1, 2, 3, 4, and then it'll have a radius of 3. Should have written this y minus 0. And I want you to have that in mind when we start talking about transformations. We move the circle around by changing this h and k here, but the h and k is what I subtract from x and y. I'm adding to it. You know what? I'm doing things out of order. That's never happened to anybody else before. Well, this will be useful on Wednesday. Chalk this up to Monday morning, right? Okay. We may actually get to this later today. This is a short subject. What we're going to talk about is average rate of change on a function. So let's talk about this example from the book. It says, the Sahara Desert from June 1st to August 15th. Anybody ever been in the Sahara Desert here? I wouldn't think so. I was in the Sahara Desert once. It was 130 degrees in the shade. It was like walking, you know how like when you open your oven, like after you've been baking something and this blast of air comes at you? That's what it was like. I used to like carry a bottle of water around and drink it constantly and never sweat. Like for 3 days I was in the desert. I never changed my clothes and I never smelled bad because I never sweat. Okay. Just personal experience adding to this crazy thing. Okay. So they describe the temperature from June to August 15th. I was in there in the middle of, I thought it was late June. You can look it up. There was an eclipse in 1973. That's when I was there. Okay, so the temperature, function of D, where D is the days from June 1st, is described as 104, that's where we start, plus 1/4 D. And just in case we have any people from the civilized world, you know, like Europe or Canada, this is Fahrenheit. It's our anachronistic way of measuring temperature. So every day the temperature changes 1/4 degree. So we would say the rate of change, I'll just abbreviate, rate of change is 0.25 degrees per day. Well, life isn't really like that. It doesn't every day. It's 1/4 degree hotter. This is an average, right? On the average, we're going to see this happen. All right. Let's look at another example that probably some of you will come more to heart. Cost of a college education in the U.S. Our C is our cost function, and Y is the year since 2015, not too long ago. Okay, the average cost of a college education, $16,000 plus, some dollar signs here, $1,000 times Y, that is every year since 2005 it goes up $1,000. So again, the rate of change here is, or the average rate of change is $1,000 a year. You might note that if you think about this in terms of our slope-intercept form, y equals mx plus b, that rate of change is the slope. That is the slope on our function. Okay. We might have a more complicated function describing some property. And it might look like this. It might look like that. And it might move up a bit. It might stay nice and flat. All right. So if we wanted to know the rate of change on, say this interval, 1, or this interval 2, or this interval 3, so forth. We know how to do that now, right? That's just the slope of these nice lines here. Yes?
Please move
Yeah. Happy to. We just, delta y over delta x, and we can say for this part of the graph, what is the slope, and that'll tell us the rate of change. Actually, the exact rate of change. But life isn't usually like that. It's much more likely we would have a graph that, might be like this, right? And we don't have, nice flat slopes that we can get the rate of change at. And a little foreshadowing here in a later class in calculus, just as we'll have tools to find these maximum and minimum, we will have tools to, at some point, find what we call the instantaneous rate of change, but we don't know how to do that right now. So for now, we're going to be satisfied with what we'll call the average rate of change, for which we have a formula. So if we have a function f on an interval a, b, so the average rate of change on that interval a, b is going to be f of b minus f of a over b minus a. So let's take 2 points on this curve here and think about what that means. We'll have a point here A and some point here B. So f of A, my f of A is over here. Yes, I'm using capital letters, so I should be consistent. And my f of B is over here. And were I to draw a straight line here, this f of b minus f of a over b minus a, that's just my delta y over delta x. That's my slope of this line which I'm using. It's an approximation, right? But this is what we call the average rate of change. So let's take a look at an example. Problem. Pure math problem. If my function is x of x equals x minus 3 squared, and I'm interested in the average rate of change on the interval 1 to 3. So using my formula, this is going to be f of 3 minus f of 1 over 3 minus 1. Well, okay, that's nice. At 3 it's 0. Square is 0. At 1 it's minus 2. And 3 minus 1 is 2. So this is minus 4 over 2 or minus 2. So for this function, the average rate of change on that interval is minus 2. Now, let's distinguish here the average rate of change from the net change. The net change on this function from 1 to 3 is just f of 3 minus f of 1, which of course is minus 4. So we have average rate of change and net change. Okay, any questions on that? Yes?
So did you say there was a difference between net change, or were you saying that they're interchangeable?
No, they're not interchangeable at all. The average change, you take the net change and divide by the length of the interval. Right? Net change is just f of b minus f of a. Make that clear in your head. Okay. Good to go. It was right. It was just a very short topic. All right. Back to transformation of functions. So the first type of transformation we're going to do is kind of like what I was doing with the circle. I was moving it around, and these are called shifts. And we're going to first look at a vertical shift in the y-axis. So let's take a look at some function y equals f of x. And we want to know what happens when we transform this to y equals f of x plus some constant, or maybe y equals f of x minus a constant. We want to know what happens when we do that. So let's take a look. Let's take a look at the function f of x equals square root of x. Well, at 0 it's 0, 1 it's 1, 4 it gets up to 2, and it continues to rise. So let's see what happens if we now change this f of x equals square root of x plus 3. All right, so at 0, square root of 0 is still 0, but if we move 1, 2, 3. At 1, same thing, we move up 3 to 4. And over here at 4, we're going to move up to 5. So what we see here is that when you add a constant to a function, that function just gets moved upwards that amount. This is, again, it's a vertical shift. Similarly, if we were to subtract some value, we could just do the easy thing, f of x equals square root of x minus 3, and we would just find each of the points would move down 3. And so in this case, we would see our function move down 3. Now, before I move on, I want to write this in a different way because something's going to happen in the next iteration that will confuse some people. And I want to try and avoid that confusion. So what I'm going to do, I'm going to take this function. I'm going to write it as y equals square root of x plus 3. That's my graph of that function. And I want to subtract 3 from both sides. So I'm going to have y minus 3 equals, and then I'm going to write this as x minus 0. I want you to think a little bit about the way a circle works. Right? With a circle, well, these two would represent what? The center of the circle. Or, if you like, how the center of the circle moves relative to the origin. Well, here we have, from these two numbers, we get 0, 3. That tells us, how does this function move? You know, the square root of x, how does it move when we go to, you know, this, to this version? Well, in the x direction, we don't move at all. In the y direction, we move up 3. Okay, I want you to keep that in mind. What I want to do now, I want to stick with the same function, f of x equals square root of x. But I want to know what happens if instead of adding on a constant to the function, what I want to do is I want to say f of x equals square root of x plus 3. I think, what's going to happen now? Well, when I added something here, it kind of moved it up. So you might have an impulse to think, oh, well, my function, it's going to move to the right. 3. And that's the mistake I want you to avoid. I want you to instead think of this as, this is y minus 0 equals square root of x minus a minus 3. That is the center of my circle, if it were a circle, is going to move minus 3, 0, the numbers I'm subtracting. And it's not, in this case, we don't have a circle, but each point on this graph is going to move that way. 1, 2, 3. Right? It's going to go 1, 2, 3. And what we're going to have is when we're going to see that when we add 3 to this, we actually, our graph moves to the left. This is a big stumbling block for people. Often, you know, I'm going to get at least one person, you know, if we do this on the exam, they're going to move it to the right when we do this. But hopefully, keep that in mind. Okay, so to summarize, we have some function y equals f of x. We transform this to y equals f of x minus h plus x plus h plus k. So my function here, well, it's going to move up k. But again, think of this as minus of minus h. It's going to move over h, and that's what the shift transformation is going to do to it. A good way to think of this again is this is y minus k equals f of x minus h. That way it's kind of clear that where we're moving is from 0, 0 to hk. All right, let's look at different examples. Just a feel for this. Let's look at the function g of x equals x plus 3 squared plus 4. So this is the function, let's just call it f for now. F of x equals x squared. But if I take, I'm going to make my g of x f of what? X minus a minus 3 and, well, I want to say minus 4, but that's going to be g of x plus 4 equals, I'm writing this all the way I don't want it. Removing this. Okay. One more try here. We want to say y minus 4 equals x minus 3 squared. So my original function is going to move how? It's going to move minus 3 in the x direction and plus 4 in the y direction. Okay? There's my 4, there's my minus 3. So if I draw my parabola, I know that it's going to go 1, 2, 3 in the x direction, and 1, 2, 3, 4 in the y direction. So it's going to look like this. In particular, the vertex here is going to be what? Well, the vertex here was 0, 0, so the vertex here has to be minus 3, 4. All right, any questions about this? Okay. All right, that's one type of transformation. The next type of transformation we want to look at is called a reflection. So you can think of a reflection as being like looking at something in a mirror. So we're going to again take this simple parabola of x equals x squared. And what we want to do is reflect it across the x-axis. We want to think of this, the x-axis, as a mirror. So 0, 0 is on the mirror, so it's not going to go anywhere. But take the point 1, 1, it's going to move down here. Negative 1, 1, it's going to move down here, and so forth. Each of these points is going to move down here. So our reflected function is going to look like this. In this case, it's an upside down parabola. So how do we do that? Well, if we transform f of x to negative f of x, and that's exactly what we're doing here. Each of these points gets reflected across the x-axis downwards. So if f of x is equal to x squared, negative f of x is equal to negative x squared. So my reflected function, let's use this. We haven't done this before. It's just a way of saying a different function like f. Put a little prime on here. So f of x, our reflected function, is now f of x equals negative x squared. Similarly, we might want to reflect something across the y-axis. So how would we do that? Well, let's take our function f of x equals square root of x. And I want to reflect it across the y-axis. So again, each point here is going to have a corresponding point over to the left. So how do we do this? Well, instead of, over the x-axis, you made f of x negative f of x. To reflect over the y-axis, we transform f of x to, again, we'll call it f of x. We transform it to f of minus x, which we'll call f prime of x. And what is that? That's just the square root of negative x. And that's exactly the graph we have here. I guess I should iterate these. So we looked at shifts, vertical and horizontal. We have a mirror image function across the x-axis, the y-axis. We could actually do this across both axes, couldn't we? You could say, I want to transform f of x to negative f of negative x. Well, what would that do? That would reflect it across both the x and the y-axis. So we have a kind of scary looking function here. F of x equals square root of 1 minus x cubed. What's the domain on this function? guess what the domain on this is? You want to tell me authoritatively? Okay. So what does it mean for me to ask what the domain of this function is? I know where this is well defined, right? So where is it not defined?
When it's negative?
Yeah, when under the radical it's negative. Okay? So how would I get a negative under the radical? Well, if I have a big negative number, like say negative 10, right? What happens? 1 minus 10 minus 1,000. Oh, that's a positive number. Oh, so big numbers are okay. Right? What about a positive number? About like say 3. 3 cubed is 9. 1 minus 9 minus 8 doesn't work, right? So negative numbers seem to be out. So where's the dividing line? Where do we go from this becoming negative to positive? Yeah?
When you put in 1?
Yeah, when you put in 1. Right? So that's going to be like an upper limit, right? But if we put in a really negative number, all the way back down to negative infinity, this becomes positive and we're okay. All right? Well, we have a starting point for graphing this. So we know the graph is going to be over on this side. From 1 to 0, what happens? Well, at 1, this is 0. 0 is 1. And in between, it kind of goes like this. And then what happens? One way to think about this is, if x was very large, the 1 wouldn't really matter, would it? In other words, it's going towards the square root of x cubed, negative x cubed, right? Which is what? Negative x to the 3/2. So this is, it's somewhere between x squared and x cubed, off in this direction. All right, so that's my f of x. Where's my f prime of x? Well, it's equal to negative f of negative x. So what's that? That's negative square root of 1 minus negative x cubed. Negative square root of what? 1 plus x cubed. All right, but what are we doing? We're reflecting each point in both axes, right? So let's take this point here. We're going to reflect it over here. But then when you reflect it in the y direction, it just stays there. This point, you know, it's going to reflect over here, stay there. And all these points here are just going to kind of come in like this. These points, again, we're going to reflect from 2 axes. Can someone close the door? Am I running over without realizing it? No. Okay, so this is f prime of x equal to negative square root of 1 plus x. Okay, that one was a bit tricky. But that's, again, now we know we can reflect in the x and y axis. one more point about all this. It's completely possible to take something, let's say a circle, and to have our mirror not be an axis, right, or even an offset axis. It could be kind of a line like this. And then, you know, if you reflect each point, right, here, 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 and so forth, you can have that kind of reflection. We are not going to do that, thankfully, in this class. That would be a bit complicated, right? But you should be aware that that's another possibility.